Hydrogen is often described as the cornerstone of the energy transition, a clean fuel that can decarbonize industries too tough for batteries or direct electrification. Politicians call it a pathway to energy independence. Companies view it as a billion-dollar growth engine. And environmentalists hope it can be one of the tools to stabilize global emissions. But behind all the flashy headlines and the massive investment numbers lies a quieter, almost mundane detail that could make or break the hydrogen economy: water. Every kilogram of hydrogen produced via electrolysis requires 9 liters of ultrapure water. That's not just 9 liters of tap water. It's water so clean that its conductivity is nearly zero, stripped of salts, metals, and organic molecules down to the parts per billion level. For a household, 9 liters doesn't sound like much. But once you scale it to industrial hydrogen projects, the numbers become daunting. A 100-megawatt hydrogen plant producing around 20,000 tons of hydrogen per year would need about 180,000 cubic meters of ultrapure water annually. And the megaprojects planned in Saudi Arabia, Australia, and the US will be 10, 20, even 50 times larger. That's millions of cubic meters of water every year, enough to rival the needs of medium-sized cities. In regions where water is plentiful, this might not raise eyebrows. But many of the best places to make cheap renewable hydrogen are also water scarce. Think of North Africa, the Middle East, or inland parts of Australia. These are sunny, windy regions where renewable power is abundant and cheap, but water isn't. Developers there often look to seawater desalination as the obvious answer. And desalination works. We've seen it at NEOM in Saudi Arabia, where one of the world's largest hydrogen plants will pair renewables with desalinated seawater. But desalination is expensive, energy-hungry, and environmentally challenging. Which raises the question, what if, instead of desalinating seawater, we tapped into a resource that cities already produce every day? That's where wastewater comes in. Across the globe, municipal wastewater treatment plants collect, treat, and discharge billions of liters of water every day. Some of it goes into rivers, some into oceans. Much of it is considered waste, even though it's already been partially treated. What if that water could be recycled, purified further, and turned into the lifeblood of green hydrogen production? At first, the idea might sound unappealing. Wastewater is sewage, industrial discharge, runoff, the stuff no one really wants to think about. But modern technology can transform this resource into water cleaner than what most of us drink from the tap. For decades, industries like semiconductors and pharmaceuticals have relied on advanced reuse and purification systems to create ultra-pure water. Applying the same principles to hydrogen isn't just possible, it may be essential. To understand why, let's unpack the chemistry. Wastewater contains a cocktail of contaminants: ammonia from fertilizers, phosphates from detergents, chlorides from household cleaning products, silica from natural erosion, heavy metals from industries, and pharmaceuticals from human use. On their own, many of these aren't catastrophic. But for an electrolyzer, even tiny amounts can spell disaster. Chlorides, for example, can corrode the catalyst layers in PEM electrolyzers, leading to costly downtime. Silica can form scale that clogs membranes. Calcium and magnesium cause fouling and increase maintenance costs. And organic molecules, if they slip through, can poison catalysts and reduce efficiency. That's why wastewater destined for hydrogen must go through a rigorous multi-barrier treatment process. It usually begins with microfiltration or ultrafiltration, which act as physical barriers to remove bacteria, protozoa, and suspended solids. Then comes reverse osmosis, the powerhouse technology that removes dissolved salts, heavy metals, and trace contaminants. To deal with persistent organics, activated carbon or advanced oxidation processes step in, breaking down molecules like pharmaceuticals and endocrine disruptors. Ultraviolet disinfection adds another layer of microbial safety. And finally, electrodeionization or mixed bed deionization polish the water to ultra-pure standards. At that point, the water's conductivity is so low it can safely enter an electrolyzer. The process might sound excessive, but it's proven. Singapore's NEWater program has been doing it at scale for years, producing water so clean it's safe to drink. In fact, Singapore meets up to 40% of its water demand through reused wastewater. That's a city-state with one of the highest standards of living on Earth, relying on a system that could one day feed hydrogen plants. The case for wastewater reuse is compelling on several fronts. First, availability. Municipal treatment plants operate continuously, and in many cities, the effluent they produce every day dwarfs the needs of hydrogen plants. In California, for example, a single treatment facility can process hundreds of millions of gallons daily. A hydrogen developer tapping just a fraction of that flow could secure a reliable water supply. Second, wastewater reuse reduces environmental discharge. Instead of releasing nutrient-rich effluent into rivers or seas, which can fuel algal blooms and harm ecosystems, the water is repurposed into a clean fuel. Third, it avoids competition with freshwater resources. In drought-prone areas, hydrogen developers face scrutiny if they draw from drinking water supplies. Wastewater sidesteps that issue. But wastewater reuse is not without challenges. The biggest is variability. Unlike seawater, which is relatively stable, municipal wastewater fluctuates. Rain events dilute it. Industrial discharges spike contaminants. Treatment systems must be resilient enough to cope with these swings without compromising output quality. That means redundancy, robust monitoring, and sometimes over-design, all of which add cost. And cost itself is another factor. Advanced reuse systems aren't cheap. Depending on location and scale, wastewater reuse might cost between $0.50 and $1 per cubic meter. For hydrogen, that translates to 0.04 to 0.09 per kilogram. It's not huge, but when projects are struggling to push costs down to 2,000 kilo, every decimal point matters. There's also public perception, the so-called yuck factor. Selling communities and investors on toilet-to-hydrogen projects requires careful communication. People need to know that the water is not just safe, but cleaner than what comes out of most taps. Transparency, education, and community engagement will be critical. Despite these hurdles, real-world projects are emerging. In California, Plug Power and other developers are exploring wastewater partnerships. The city of Lancaster has signed agreements to supply treated wastewater for hydrogen production, turning municipal effluent into a revenue stream while advancing clean energy goals. In the Netherlands, pilot projects are experimenting with wastewater-fed hydrogen, leveraging the country's advanced water management expertise. And in Asia, where water reuse is already part of national strategies, it's only a matter of time before hydrogen projects join the mix. Technology vendors are also moving quickly. Global water leaders like Veolia and Suez are adapting advanced reuse systems for hydrogen plants. Membrane giants like Toray and DuPont are supplying ultrafiltration and reverse osmosis technologies capable of handling variable wastewater feeds. Evoqua is providing advanced polishing systems, while SnowPure is targeting electrodeionization for ultrapure output. What we're seeing is a supply chain that has already mastered these technologies in other industries, semiconductors, pharmaceuticals, power plants, now positioning itself for the hydrogen boom. When comparing wastewater reuse to seawater desalination, the differences are striking. Desalination plants are capital-intensive, often costing $1,000 to $2,000 per cubic meter per day of installed capacity. Wastewater reuse systems can be built for half that. Energy requirements are also lower, since wastewater has far less salinity than seawater. On the flip side, wastewater requires more pre-treatment and monitoring. But overall, the economics lean in favor of reuse, especially for inland projects far from the coast. Beyond economics, wastewater reuse aligns with sustainability goals. Cities under pressure to recycle water see hydrogen as an anchor customer. Hydrogen plants, in turn, gain social license by contributing to water security instead of competing with it. It's a model that benefits utilities, developers, and communities alike. Still, regulations remain a hurdle. Wastewater reuse is tightly controlled in many jurisdictions. Developers must secure permits, meet strict monitoring requirements, and in some cases, navigate competing claims for the same water. Agriculture, industry, and municipalities all want access to recycled water. As hydrogen scales, these allocation debates will intensify. Looking forward, innovation promises to make wastewater reuse even more attractive. Advanced oxidation processes are getting cheaper and more effective. Nanomaterial membranes like graphene-based filters promise higher selectivity at lower energy costs. AI-driven monitoring systems can adjust treatment in real time, improving efficiency and reducing chemical use. And on the horizon, direct wastewater electrolysis, where contaminants are oxidized at the anode while hydrogen is produced at the cathode, could bypass much of the pretreatment altogether. For developers and investors, wastewater reuse is not just a technical curiosity. It's a strategic decision. In arid regions, it may be the only option. Even in water-rich areas, it enhances sustainability credentials and helps win community support. For municipalities, hydrogen creates a new value stream for water that would otherwise be discarded. And for vendors, it represents an emerging multi-billion-dollar market. The bigger picture is clear. The hydrogen economy is not just about renewable electrons and electrolyzers. It's about the infrastructure that supports them: pipelines, storage, and yes, water systems. Without sustainable water supplies, hydrogen projects will stall. With wastewater reuse, they gain a reliable, circular, and socially acceptable foundation. If you're a developer, consultant, or investor, don't overlook this. Incorporate water strategy into your feasibility studies. Model wastewater reuse alongside desalination and municipal supply. Understand the vendor landscape. Engage regulators early. And above all, communicate transparently with communities. Because in the end, hydrogen's success will depend not only on cost curves and technology, but on public trust. For those ready to go deeper, we've built tools to help. At h2hub.reneenergy.com, the Green Hydrogen Project Development and Financing course and the H2Hub Schematic Generator give you the ability to model water treatment pathways, assess CapEx and OpEx, and understand how decisions about water ripple through entire projects. It's a hands-on way to see how wastewater reuse, desalination, or municipal supply fit into the economics of hydrogen. Hydrogen may be the fuel of the future. But without water, there is no hydrogen. And without innovative approaches like wastewater reuse, the future of hydrogen may remain just out of reach. The question isn't whether wastewater can power hydrogen. The question is whether we're ready to embrace it as one of the keys to scaling a truly sustainable hydrogen economy.